All right, we're going to talk about the different classes of levers. There's 3 classes of levers, and really it comes down to where is the fulcrum. So in the first class lever, the fulcrum is in the center, and we have an effort force on one side and a resistance force on the other. And we want to calculate ideal mechanical advantages for these different types of levers. And if you remember, ideal mechanical advantage is the effort distance over the resistance distance. If you remember, the way I remember that is ideal. There's dE, so that goes on top. Ideal mechanical advantage is dE over dr. So what is the ideal mechanical advantage for a first class lever? Well, in this case, right here, in this particular lever we drew right here, the effort distance right here, you can see is greater than this resistance distance. So that means ideal mechanical advantage for that one would be something greater than 1, right? It'd be something greater than 1. What if we redrew this and we had a lever and it was exactly in the middle of our resistance force and our effort force, so exactly in the middle. Well, the distance to the effort over the distance to the R would be the same, and that mechanical advantage would be equal to 1. So a first class lever can have a greater than 1 mechanical advantage and an equal to 1. Well, I guess also I could, what if I put the fulcrum even further towards the effort? So here's the fulcrum, and here is the lever, and my effort's over here, and the resistance force is over here. Well, now the dE is less than the dr, so this numerator would be less than this denominator, and you would get a mechanical advantage of less than 1, which you probably wouldn't want to use very often. But the levers, the first class lever can have a mechanical advantage greater than 1, equal to 1, or less than 1. Mechanical advantages can never be less than 0, so for anything, so we don't worry about that. But for this one, depending on where the fulcrum is, if it's really close to the resistance force, which is normally what you want to do, you're going to get a mechanical advantage of greater than 1. That's going to be very helpful. If it's exactly in the middle, you'd have a mechanical advantage of 1. You're going to basically put the same amount of effort in as you're going to take to lift it anyway. And then if the fulcrum is really close to the effort force, in this situation down here, then you're going to have a mechanical advantage of less than 1. So a first class lever, the fulcrum's in the middle, and you can have a mechanical advantage of basically anything. All right, second class lever, the fulcrum here is on the end, and you're going to have a resistance force here in the middle, and you're going to lift maybe out here on the edge. And again, the IMA is effort distance over the resistance distance. What is your mechanical advantage going to be for a second class lever? In a second class lever, your resistance force is in the middle. So we think about what's in the middle. The resistance force is in the middle for a second class lever. What's your ideal mechanical advantage going to be? Well, in this case, your effort force is always going to be farther away from the fulcrum than your resistance force is, right? So if I measure the distance out to the effort force, it would be that distance there, right? What's the distance to the resistance? It would be that distance there, because we're always measuring from the fulcrum. So dE is always going to be greater than dr for a second class lever. So the mechanical advantage, the ideal mechanical advantage, is always going to be greater than 1. It's always going to be greater than 1. If I go back to the last one, I want to make sure I wrote that. Yeah, I wrote those symbols correctly. Okay. So the ideal mechanical advantage of this one is always going to be greater than 1 for a second class lever. You might ask, what is a second class lever? When would we use it? Well, an example of one would actually be a wheelbarrow. So I have like a, how does this work? You got something like this, and it's not very good, but there we go. There's a wheelbarrow. Okay, where's the resistance? Well, your load of dirt or something is in here. That's your resistance. Your fulcrum is down here, basically the wheel. And what are you doing? You're applying your effort force on the handles. So that would be an example. A wheelbarrow would actually be an example of second class lever. And you always get an ideal mechanical advantage of greater than 1. This is helpful to take large loads places. Okay, a third class lever is usually the one that people have a hard time thinking about. It's kind of strange. Your effort force is actually in the middle. So, ideal mechanical advantage, again, is dE over dr. Okay, and what's the case here? Well, your distance out to your effort force is going to be from here to here, and your distance out to your resistance force is going to be from here out to there, right? So in this case, your dr, your denominator, is always going to be greater than your numerator. And what does that mean? That means your ideal mechanical advantage is, for a third class lever, is always going to be less than 1. Less than 1. That's kind of strange. It's going to be less than 1. So, why would you ever want to do this if you're going to have an ideal mechanical advantage of less than 1? Well, the reason is you want to go ahead and put in a big force through a small distance, because you want to actually get your resistance force to move a larger distance. You're not caring about applying a big resistance force. You're wanting to actually get a lot of distance out of this. What is an example of this? This would be basically playing a lot of different sports. Think about a baseball bat, and you're going to swing a baseball bat. This is like a lever. Where's your fulcrum? Your fulcrum is like here where your hands are. You put your hands here, there's your fulcrum. Okay, there's your fulcrum. Or actually, sorry, that wouldn't be right. Your fulcrum is down here. It's the edge of the end of the bat. Here's your fulcrum. Where are you applying your effort force? That's where your hands are. Your hands are right here on the bat, and you're applying an effort force here to move the bat forward. And where's the resistance? Well, the resistance is where the ball is going to come out here and it's going to hit. There's your resistance force. There's your R. Here's your E. And then this down here is your fulcrum. Okay? You see that? How that works? So, you're applying an effort force down here, and so that you can move the resistance force out here where the ball hits, you can move this bat here through so you only have to move this part of the bat through a small little circle. But this one then will get moved all the way around. See, and that's what you want. You want to really be able to apply a force down here so that you can move the end of the bat through a big, long, sweeping circle and really, really fast. You want to move that really, really fast. So when it hits the ball, it makes the ball go a long ways. So this is actually an example of a third-class lever. And yes, sometimes you want to increase the end of the bat's distance or its velocity rather than multiplying the force. It doesn't take a lot of force to make the ball move, to hit the ball. So we don't really worry about multiplying our force. We want to multiply our distance that we're doing. So we're going to kind of have a reverse situation here. So that's a third-class lever. The IMA is always less than 1. So review this a little bit. So here's how you can remember it. This is a first-class lever. And what's in the middle? The fulcrum. The fulcrum's in the middle. This is a second-class lever. What's in the middle? The resistance is in the middle. This is a third-class lever. What's in the middle? The effort. So the way I try to help people remember it is free, F-R-E, free, 1, 2, 3, free, 1, 2, 3, free, 1, 2, 3. First-class lever, the fulcrum's in the middle. Second-class lever, the resistance is in the middle. Third-class lever, the effort's in the middle. That's how we can remember that. And then what about mechanical advantages? For the first-class lever, mechanical advantage can be anything, right? It can be greater than 1, it could be equal to 1, or it could be less than 1 for a first-class lever. Second-class lever, it's always going to be greater than 1. And third class lever, it's always going to be less than 1, your mechanical advantage. Because on the third class lever, remember, you're trying to get your distance. You're trying to get your distance out of it rather than the amount of force. Okay, so those are the 3 classes of levers. Hopefully you can remember which one is which with free 1, 2, 3.